Alright, so we're going to talk about significant figures in this video. We're also going to go over exercise A, exercise B, and conceptual example 1-2 from chapter 1 in your textbook. In this lecture, hopefully you're taking a look at this after you looked at the measurement and uncertainty video, because the measurement and uncertainty video covered how you report a number that you've measured or recorded according to its accuracy and according to its precision. And we're going to talk in this video about what significant figures are and how we use them to manipulate data and to express data in a laboratory or calculation setting. So the first thing to know is, let's take a look at the definition of significant figures, and I will work on this focus a little bit for you. But significant figures are the number of reliable known digits in a number. And like I said, we're going to get that nice and visible for you. It just doesn't want to. So the number of reliable known digits in a number. And we're going to take a look at how to identify known digits in a number. And in this lecture, we're not going to be looking at how we got the numbers that we wrote down. If you want to know how many numbers to write down when you're reporting an answer from values that you measured, then make sure to take a look at measurement and uncertainty, the previous lecture. For significant figures, we're going to take these two numbers, and these two numbers were reported. We are going to pretend that they were reported as data from a lab. So somebody went and they measured these two numbers, and they said with the measurement tool that they had that these were as correct as possible. So we could consider in the laboratory that this 23.21 centimeters is accurate plus or minus 0.01 or 0.02 in the hundredths place. And this 0.0062 centimeters is accurate to the plus or minus 0.001 or 0.002 in a hundredths place for the tool that was measured. That's how those numbers were generated. We're just going to talk about how many significant figures each of these numbers has. 23.21 centimeters is given by 1, 2, 3, 4 digits. Therefore, this number here has 4 significant figures. 0.062 has 2 non-zero digits. All right, I'm going to say that this number here has 2 significant figures. You might ask, wait, what about these zeros right here? And I'm going to point out something that I really want you to remember, and that is that these zeros right here, they come before these non-zero numbers. And when I say a non-zero number, I mean any number that's not a zero. These zeros here completely precede all of the non-zero numbers. That means that they're just placeholders for a decimal. In fact, if I have 0.062 centimeters, that's the exact same thing as saying 0.62 millimeters. Right? Because there's 10 millimeters in every centimeter. If I have 0.062 centimeters, I have 0.62 of a millimeter. I didn't change the number of significant figures. Here there's still 1, 2. Those zeros were just holding the decimal place for us. Therefore, those are non-significant zeros. And that's true for any zero that precedes the non-zero digits. So that's how you're going to be identifying how many digits or how many figures are significant in any written number. But let's say that you have to calculate with them. If in that same laboratory experiment you took a measurement that was 11.3 centimeters, and let's say that that's a length, and here's a width of 6.8 centimeters. right? If we want to find the area, all right, area is length times width. So we're going to just do some really simple math. Length times width is going to be 11. Let's get that light off. Oh, no good. So it's going to be 11.3 times 6.8, and that's what gives us this 76.84. And that's the area. And remember, it's centimeter times centimeter. So just like x times x gives us x squared, centimeter times centimeter gives us centimeter squared. So this is the calculated area of whatever object we've measured in the laboratory. But hold on. Remember that while this is a correct calculated value, if we take a look at this 11.3 and 6.8, we only had accuracy to the 10th place, right? This could be any number from 11.2 to 11.4, given the range that's suggested or inferred by the uncertainty of this number. And this one here could be 6.8, 6.7, or 6.9, given the range that's shown by writing this number down. So let's take a look at what that means about our range for the actual area, right? If we're looking at an accurate uncertainty of plus or minus 1, then that means that we could have a range where the length was actually, instead of 11.3, it was 11.2 because of that plus or minus uncertainty. And the width could be on the low end 6.7 centimeters because of that plus or minus uncertainty. Well, that means that on the low end for area, we could have 11.2 times 6.7 centimeters. And that's going to give us a value of 75.04 centimeters squared. And remember, comparing these two numbers, you can see the difference. And that tells you that for certain, that 8 and that 4 probably aren't very significant, since these two numbers have that plus or minus 0.1 uncertainty, and that plus or minus 1 uncertainty gave us this number this small. Conversely, on the upper end of the range, we could have a value of 11.4 centimeters times 6.9 centimeters, and that would give us an area of 78.66 centimeters squared. Now think about this massively wide range here, right? This is on the low end and this is on the high end, and any number with these values that we have here, any number that falls in between these would be, in theory, an accurate enough, a correct enough answer given the uncertainty in our original measurement. So we have a problem. Because our uncertainty gives us a range between 75 and 78, that means that the best we can say is that the answer is 77 centimeters squared, right? And let's talk about why we can say that that's the best answer. Why is it that these tenths places and hundredths places are completely worthless to us? Well, when we talk about our uncertainty, now our uncertainty is in the ones place, right? So that means that our uncertainty is 77 plus or minus, and we're going to say 2. This makes sense because 77 plus or minus 2 on the low end gives us a value very close to our lowest range. And 77 plus 2 on the high range gives us a number close to our high range 78. Therefore, this is really as good as we can do. We can't claim to have any more accuracy. We can't claim that these decimals, the 10th place and the 100th place, we can't claim they're significant because they aren't. So we need a rule for calculating, multiplying, and dividing when we have a limit or when we have uncertainty in our given values. And so I'm going to give you that rule. And again, just like before, I'm going to have to fuss with the paper so that it fits clearly onto your screen. And I really recommend that you do jot down this rule because it takes a little bit of practice. I'm going to be honest with you and tell you that significant figures takes time. The more you practice using significant figures correctly, the better you're going to do. But you're going to have to practice, which means that you're going to refer back to this rule more often, toward the beginning at least. So our rule for calculating and keeping the correct number of significant figures. The final result, that's our answer. That's this guy right here. Right? The final result of a multiplication or division. So anytime you're timesing or dividing, anytime you're finding a product or you're dividing, the final result should have only as many digits as the number with the least amount of significant figures used in the calculation. That's the rule. I want to bring us back up to this example. All right. If I count the total number of significant figures, 11.3 had 3 significant figures. 6.8 had 2 significant figures. Our final answer, remember the best we said we could do? This number right here has 2 significant figures. So it turns out that this rule actually guides us very well, given the range of error, the range of uncertainty that we could potentially have. This is a really nice, convenient rule, because instead of getting a number and finding the low range and the high range, we're just using the significant figures that we're limited by to very quickly truncate our number at the appropriate spot. That seems pretty easy. It's a lot easier than having to do this calculation for every single laboratory analysis that we'll ever do. Let's take a look at exercise A, which is an example, a direct example of practicing using significant figures. In exercise A, we're going to find the area of a rectangle 4.5 centimeters by 3.25 centimeters. And the book actually gives you options A, B, C, and D. I'm going to solve this problem here without using the multiple choice options, but feel free to take a look at them. And you might even be able to solve the problem without calculating the answer mathematically. But I'm going to show you how it's done mathematically. First things first, you want to do the math. So whether you're doing it on paper or you're like me and you're lazy and you're going to do it on the calculator, you want to put in the numbers as they're given to you. So it's going to be 4.5 times 3.25. And that gives us this answer, 14.625 centimeters squared. Now, remember, I got the centimeter squared because it's a product. Centimeter times centimeter is centimeter squared, just like x times x is x squared. Now, this answer right here has 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 5 significant figures. And given the range calculation that we did before, we could say pretty certainly that this answer has too many significant figures. So we're going to truncate it just based off of the number of significant figures in the measurement values that we're limited by. 4.5 centimeters has 2 significant figures. And 3.25 has 3 significant figures. And our rule says that the final result of multiplication or division should have only as many digits as the number with the least amount of significant figures. used in the calculation. The number with the least amount of significant figures was this 4.5 centimeters, 2 significant figures. And so that guides us. That tells us that our answer is only going to have 2 significant figures. Everything else is going to be truncated. It's going to be rounded away. Rounding this number to have only 2 significant figures means that we're rounding to the ones place. And general rule, any time when you're looking at rounding at a place, if this number right here is 5 or over, you want to round up. If this number here is under 5, you want to round down. So that means that this answer rounds down to 15 centimeters squared. In your textbook, that's option D. So that's multiplication and division, but those are not the only type of significant problems that you're going to have to manipulate. You're also going to be adding and subtracting. And so we're going to take a look at how the rule is different when you're adding and subtracting. And I always think that when you're adding and subtracting that this is a little bit more intuitive. So when you're adding and subtracting numbers, the final result is no more accurate than the least accurate number used. So here we're not having to count how many total significant figures. We're just looking at the overall accuracy of a number. I'm going to do a straight subtraction example, 3.6 minus 0.57. 3.6 minus 0.57 gives us the value 3.03. It's very important that you remember that your calculator does not do significant figures for you. In fact, your calculator doesn't even know what significant figures are. If you have your calculator set to round off at a certain decimal place, I recommend that you remove that feature from your calculator. You always want to make sure that you're the one deciding which figures are significant and which figures to carry forward with you, either in your data reporting or in your calculation. So this is a numerical answer. It does not have the correct number of significant figures. We have to compare 3.6 and 0.57, and we have to decide between these two which one is the least accurate. Think about it like looking on a meter stick. And so here's our tiny little example meter stick. Imagine, if you will, that you have 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, and that's a 4. All right, so on this meter stick right here, on this tiny little piece that we're taking a look at, 3.6 would be right here. If this was the instrument that we were using, we would be able to go beyond saying it was 3.6. We would actually be able to say that this is 3.61 or 3.62 or 3.60, depending on how close we were able to estimate where our measured object came in. Which means that, in truth, this first number was measured with a tool that looked more like this. It had a mark for the 3, it had a mark for a 4, and we had to estimate that if this was the halfway mark, we're maybe 0.6, not 3.5. And so this number right here is limited by this type of a measurement. 0.57, on the other hand, suggests that we were able to estimate using these next step down markings, right? That means that 0.57 was done up here. 0.57 is the more accurate number. And that means that anytime we're actually comparing numerical values, the number with the least decimal places is the least accurate of the numbers. So that's the one that's going to limit the accuracy of our answer, which means that we're actually going to have to truncate our answer or round our answer in the tenths place, which makes the most correct answer we could give for this problem 3.0. That's how we're going to be using addition and subtraction for significant figures. Let's take a look at exercise B, where we're going to actually look at what kind of accuracy different numbers have. Here we're going to look, do 0.00324 and 0.00056 have the same number of significant figures? Well, that's a good question. The number of significant figures here, remember, includes all non-zero digits and none of the zeros preceding the non-zero digits. So that means that 0.00324 only has those three non-zero numbers. All of these zeros don't count as significant figures, they're decimal placeholders. So that means that this has 3 significant figures. On the other hand, 0.00056, so I'm going to have to modify my number, 0.0056, right? This has 2 non-zero numbers. Even though there's 1, 2, 3, 4 zeros preceding those non-zero numbers, none of them are significant because they're all just holding that decimal place. All right, so that means that this one only has 2 significant figures. All right, 0.00324 has more significant figures than 0.00056. But if we line them up, even though this has 3 significant figures and this has 2 significant figures, those numbers have the same amount of accuracy for addition and subtraction because both of these numbers go out to the same decimal place. The same tool was used, the same tool capabilities was used to obtain those numbers. So it's really important to remember and distinguish the difference between the total number of significant figures and where the accuracy in that number lies. And exercise C from your textbook does a really good job of helping you break it down. So we're going to take a look at exercise C to finish off this talk. All right, exercise C has us take a look at 3 different values. And if you take a look at these 3 different values, you're going to notice that there's not a lot that's different about them. In fact, the only thing that's really different about them is where the decimal place is, the decimal placeholder. And so we're going to take a look for each of the following numbers, state the number of significant figures and the number of decimal places that it has. So for A, we have 1, 2, 3 non-zero numbers. This is 3 significant figures. And the decimal places that it has, we're actually looking at the 10th place and the 100th place. So that means that this number only has 2 decimal places. B, we look at all of the non-zero numbers, 1, 2, 3. So this one has 3 significant figures, but this time we have a decimal place, tens, hundreds, and thousands. So we have 3 decimal places. In fact, this is a really important thing to make a note of because even though the number of significant figures are the same, if these 2 values have the same unit, we could say that B is a more accurate number than A if they have the same unit. And we're going to talk about units in our next little video. And then finally, C, if you guessed 3 significant figures, you were right. This time we have 1, 2, 3, 4 decimal places. Right? So again, if A, B, and C all have the same unit value, that makes C the most accurate of these numbers, even though they all have only 3 significant figures. That's one of the most important distinctions between the total number of significant figures and the total number of decimal places. This is an important consideration when we're looking at addition and subtraction with numerical values. Last but not least, we're going to take a look at a conceptual example. And I like this conceptual example because it actually gives us a chance to look at something that you might see in a laboratory setting, especially if you're having to do some measurements. Having something written on paper like this is actually probably going to be a little bit easier to measure than if you're in the laboratory and you're trying to take a measurement. So imagine that this is a sharp angle. We're going to use a protractor to measure that angle, and we're going to determine using our protractor, and hopefully I'm really hoping that this will show up nicely, and it does. And we're going to zoom in on it. And you should be able to see right here that this angle, if we set it at the 0 mark, measures out to be 30 degrees. So this is a 30-degree angle. But we need to decide, using this measurement, we need to decide how many significant figures you should quote for that 30-degree angle. And in order to do that, we have to decide, well, how precise exactly is our measurement? And this is a really neat kind of example, because if you take a look at this protractor right here, you're going to see the actual tick mark on the protractor and the pin are pretty darn close to the same width, which means that it's really difficult for me to tell if I wouldn't be able to tell if it was 30.1 or 30.2 or 30.3. I can tell that it's 30, and because the line is just as wide as the measurement tick, it's difficult for me to tell beyond that. So that means that the correct amount of significant figures for this measurement is just going to be 30. Right? 30 degrees. The 3 and the 0 are significant. We're going to be able to say that it's plus or minus 1 or 2. Alright? So it's not 30.0, it's 30. We have two significant figures here. You can also, for help making your way through this problem, you can also go ahead and take a look at figure 1-7 in your textbook on page 7 that shows you another measurement very similar to the one that I've done up here. So we've decided that two significant figures is appropriate. And because two significant figures is appropriate, what if we had to find the cosine of that angle? What if we had to do a little bit of calculation with this? We needed, this is a 30-degree angle down here, and we needed to know what the cosine of 30 degrees was. Cosine of 30 degrees. Before you freak out, this is a really simple calculation to do on your calculator. You're just gonna take that angle 30 degrees and you're gonna take the cosine of it. That's how simple it is. If you don't know the relationships or the ratios given by sine, cosine, and tangent, we will get there. But it's just important for you to know this is a calculation, and this calculation is done with an actual physical measurement. This number had a limit. So that means that the cosine of 30 degrees, according to our calculator, is 0.8660254. And I could go on to say 404 if I wanted, but I'm going to stop there because I think you all probably should have a good idea right now that most of these digits aren't really going to be very helpful to us. You see, we only had an accuracy of plus or minus 1 degree. So that means that when we take the cosine of this 30-degree angle, we only have that accuracy within plus or minus 1 degree. So we're going to use the multiplication and division rule, and we're going to look at the total number of significant figures. Total number of significant figures here is 2. We're limited by that place. Therefore, the cosine of 30 degree using our rounding is going to stop at the second significant figure, which means that the cosine of 30 degrees is actually going to be 0.87. All right, and that's going to be our numerical ratio number. All right, and that 0.87 was limited by our ability to accurately measure this 30-degree angle. If we'd been able to measure the angle as 30.0, then our cosine of 30 answer would have been 0.866. So it's very important for you to take a look at what your given numbers are to calculate and to report your answer correctly. So those are our significant figures. There is going to be practice coming up with them, but I want to make sure that you have this information. You should have it in your notes. If you haven't worked out these conceptual examples in your notes, or if you haven't included these important definitions that I've given you, I really do recommend that you follow along, you take these notes with the videos as we go.